Hi students, have a nice day. Let's continue with the gas laws. In the last session we discussed about the Boyle's law and Charles law and its application. And different plots versus pressure versus volume, then volume versus temperature, then pressure volume graph at a constant temperature is known as isotherms. Then a volume temperature plot at a constant pressure is called isobars. So in this section, first we discussed about the Lussac law. Lussac studied the pressure and the temperature relationship at a constant volume. And he proposed that the pressure is directly proportional to the absolute temperature of the gas at a constant volume. Once again, Lussac studied the relationship between the pressure and temperature of a gas at a constant volume, and he understands that pressure is directly proportional to the absolute temperature of the gas at a constant volume. So, let's define the Lussac law. At a constant volume, the pressure of a given mass of gas is directly proportional to its absolute temperature. Once again, at a constant volume, the pressure of a given mass of gas is directly proportional to its absolute temperature. Okay, let's represent this in the mathematical way. Pressure of the gas is directly proportional to the temperature for a given mass of gas at a constant volume. The volume is constant. Okay. Volume must be constant, you remember that. Then we can remove the proportionality by using the constant K. K3. K1 for Boyle's law, K2 for Charles law, K3 for Lussac law. So K3 into T. Okay. Then this is a mathematical representation. Or we can say that P by T is equal to a constant. P by T is a constant. For a gas, the initial pressure P1 and its initial temperature T1 is changed into final pressure P2 and temperature T2. So P1 divided by T1 is a constant. Similarly, P2 divided by T2 is a constant. So let's equate the equation, two equations. Okay, the right side is same. So we have to write P1 divided by T1 is equal to P2 divided by T2. Or P1 by P2 is equal to T1 by T2 at a constant volume. Okay, both equations are correct. At a constant volume, P1 by T1 is equal to P2 by T2. Rearranging the equation, P2 brings here, T1 goes to the right hand side. P1 by P2 is equal to T1 by T2. That is, P is directly proportional to temperature. P1 is directly proportional to T1 and P2 is directly proportional to T2. Are you clear? Yes. Then let's make a plot. Pressure versus temperature. Okay, pressure versus temperature. This is the volume V1, constant volume. Constant volume V2, constant volume V3. Volume must be constant. Okay. pressure and temperature varies. Pressure is directly proportional to the temperature. When pressure increases, temperature increases. Here, the V1 is less than, V2 is less than V3. Okay, volume must be constant. This plot is pressure versus temperature at a constant volume V1. This line is pressure versus temperature at a constant volume V2, and this plot or line pressure versus temperature at a constant volume V3. Here V1 is less than, V2 less than V3. Remember that. And in this plot, the volume must be constant. And such plots are called isocores. Isocore. Or it is sometimes known as isometric. Okay, mainly or usually we are called isocores. So what are isocore? Isochoric process means the process takes place at a constant volume. So isocores are the plots pressure versus temperature at a constant volume. Okay, each lines are called isocores. Are you clear? Yes. So that's about the Gay-Lussac law. We just understand that pressure is directly proportional to the temperature. And we move to the application of Gay-Lussac law. I think the automobile tire is inflated by normal air or nitrogen. In summer season, the automobile tire is less inflated than the winter season. Okay, boys know these things, some girls also. When the air is filled in the automobile tire, we know that at summer season the temperature is higher. And when we inflated the tire by more pressure, there is a chance for bursting the tire. Okay, the tire will be burst because when pressure increases, temperature increases. Already the temperature is high in the summer season, and if you increase the pressure, it should be damage the tire. So remember that in summer season the tire is less inflated than the winter season. Okay. The next application is pressure cooker. Pressure increases, the temperature inside the cooker also increases. Okay. So pressure cooker is another application. Then we move to the another law, Avogadro law. This is we already discussed in the chapter 1. Avogadro law. What is Avogadro law? What is Avogadro law? Avogadro law is the relationship between volume and amount of substance at a constant temperature and pressure. Okay. So, in that chapter we state Avogadro law. This is a relationship between volume and amount of substance, amount of gas. The amount of gas is expressed in number of moles. Okay, these things we discussed in the first chapter. The amount of substance unit is mole. Yes, let's define the Avogadro law. Equal volumes of all gases contains equal number of molecules at a constant temperature and pressure. Once again, equal volumes of gases contains equal number of molecules at a constant temperature and pressure. Let's express in a mathematical way. V is directly proportional to the number of molecules. Okay, equal volumes contains equal number of molecules at a constant temperature and pressure. Okay, so number of moles is directly proportional to number of molecule is directly proportional to the number of moles. Okay, the number of mole is equal to number of molecules divided by Avogadro number. These things you know that. Number of moles can be calculated from the number of molecules. Number of moles is equal to number of molecules divided by Avogadro number. So let's write V is directly proportional to the number of moles, or V is equal to K4 into number of moles, another equation. Okay, so this is Avogadro law. Already we discussed, that's why it's a simple concept. Volume is directly proportional to the number of molecules. Number of molecule is directly proportional to the number of moles at a constant temperature and pressure. So let's write V is directly proportional to N, or V is equal to K4 into number of moles. Okay, so number of mole increases, number of moles of gas increases, volume also increases. Yes, next is ideal gas. A gas which follows Boyle's law, Charles' law and Avogadro law strictly is called ideal gas. Once again, a gas which follows Boyle's law, Charles' law and Avogadro law strictly is called ideal gas. There is no such gas. It is a hypothetical gas. Real gases are not ideal. It is assumed to be the real gases behaves ideally at a certain conditions, at a certain circumstances. Are you clear? Okay, so what is ideal gas? An ideal gas which follows Boyle's law, Charles' law and Avogadro law strictly. There is no such gases. Hypothetical concepts. Real gases behaves ideally at a certain circumstances or at a certain conditions. Okay, next we discuss ideal gas equation. Okay, ideal gas equation. According to Boyle's law, we know that V is directly proportional to 1 by P at a constant temperature. Okay, what are ideal gas? Ideal gas which obeys Boyle's law, Charles' law, Avogadro law. So according to Boyle, V is directly proportional to 1 by P. Definition: V is inversely proportional to pressure of the gas. Okay. The next, according to Charles' law, V is directly proportional to temperature at a constant pressure. Okay. Then, according to Avogadro, V is directly proportional to number of moles N at constant temperature and pressure. Temperature and pressure. So, an ideal gas which strictly follows or obeys Boyle's law, Charles' law and Avogadro law. Look at this. The left hand side is volume. Okay. So, let's equate. Let's give one equation 1, 2, 3. From 1, 2, 3, let's write V is directly proportional to T, N directly proportional. So N into T. V is inversely proportional. V is inversely proportional. So V is directly proportional to NT by P. Okay. So the proportionality is removed by a constant R. As earlier we put constant K, here we write R. R N T by P. Rearranging the equation, PV is equal to R N T. Okay, again PV is equal to nRT. PV is equal to nRT for our convenience. PV is equal to RNT, no problem, but for a rhythmic saying, PV is equal to nRT. Then this is known as ideal gas equation, where R is known as universal gas constant. R is known as universal gas constant. A very simple concept. Once again, V is directly proportional to 1 by P at a constant temperature. V, according to Charles, V is directly proportional to T at a constant pressure. According to Avogadro, V is directly proportional to number of moles at a constant temperature and pressure. From these three, okay, we can equate V is directly proportional to NT by P. So V is equal to R NT by P. Proportionality is changed into constant. Here R is universal gas constant. Then rearranging the equation, P comes here. PV is equal to nRT. Okay, or RNT. Okay, RNT. Then PV is equal to nRT. So PV is equal to nRT is ideal gas equation. This equation is known as ideal gas equation. Then R is universal gas constant. A very important concept, ideal gas and ideal gas equation. Remember that a perfect ideal gas not exists. Real gas behaves ideally at a certain condition. Okay, at a very low pressure and high temperature, real gas behaves ideally. Yes, let's discuss the values of R. We know that PV is equal to nRT. PV is equal to nRT. What is R? R is equal to PV divided by NT. So R represents work done per Kelvin per mole. Okay, what R represents? Work done per Kelvin per mole. Okay, just explain how it is work done. Pressure is force per unit area. What is pressure? Force per unit area. Then volume is, in the cuboid it is A cube, or generally we can say that length cube. So force per area into length cube. By rearranging, it is force into length or force into displacement. What is force into displacement? It is work done. And in the denominator, number of moles and temperature Kelvin. So R represents work done per Kelvin per mole. Okay? Yes. So the dimension of R is energy per Kelvin per mole. Okay, work done is expressed in energies. The R value depends upon the values of pressure, volume, then number of moles and temperature. Pressure is, okay, first value R is equal to 0.08314 liter barometer Kelvin inverse mole inverse, or mole inverse Kelvin inverse, no problem. How? If the pressure is in the barometer, 1 barometer, okay, and the volume of the gas is 22.42 liters, divided by number of moles, so 1 mole at a standard temperature, okay, it is 273.15, 0 degrees Celsius or 273.15 Kelvin. So here mole, here Kelvin. So the R value is 0.08314 liter barometer Kelvin inverse mole inverse. Very clear? Then R value is equal to 0.0821 liter ATM. If pressure is written in ATM, okay, ATM, the unit is, the value is 0.0821 liter ATM, Kelvin inverse, mole inverse. Okay, yes. Then R is equal to, R value in energy in joules, it is 8.314 joule per mole. Joule per mole, mole inverse. Okay, the value is 8.314 joule per mole. Joule, Kelvin inverse. Okay, sorry. Joule, Kelvin inverse, mole inverse. Same. Okay, this energy is joule, Kelvin inverse, mole inverse. Sorry. And the value is expressed in calorie. R is equal to 1.987 calorie Kelvin inverse mole inverse. It is equal to 1.987, 1.99. Okay, 1.99, it is approximately 2 calorie Kelvin inverse mole inverse. Okay, 2 calorie Kelvin inverse mole inverse. Are you clear? So the value of R depends upon the values of pressure P, volume V, the number of moles and the temperature. Are you clear? So you memorize these values. 0.0821 liter ATM. 0.0831. Here 21, here 31. Okay, liter, barometer, Kelvin inverse, mole inverse. When energy term comes, 8.314 joule, Kelvin inverse, mole inverse. Okay, so it's very important you keep it in your mind. Next is combined gas equation. As we know that ideal gas equation PV is equal to nRT. For a fixed amount of gas, that means N is constant. Okay, for a fixed amount of gas, the variables pressure, volume and temperature. The variables pressure, volume and temperature is changes from P1, V1 and T1 to P2, V2 and T2. Okay, pressure, volume, temperature varies. N is fixed, that is N number of mole is fixed. R is also constant. So variables are pressure, volume and temperature. And it varies. P1, V1, T1 varies into P2, V2, T2. Or it is initial variables, initial condition, that one is final condition. Let's use this equation. PV by T is equal to NR, isn't it? T brings here, PV is equal to NR. Then P1 V1 by T1 is equal to NR. Similarly, P2 V2 by T2 is equal to NR. Because N is fixed amount of gas. N is fixed, R is already constant, universal gas constant. Then the right side is same. The right hand side of two equation is same. So let's write P1 V1 divided by T1 is equal to P2 V2 divided by T2. This is called a combined gas equation. Combined gas equation. Okay. So Boyle's law, Charles' law, Avogadro law combines, we get combined gas equation P1 V1 divided by T1 is equal to P2 V2 divided by T2. So that's about the ideal gas equation. In the next section, we will discuss some problems, numerical problems based on the Boyle's law, Charles' law, Avogadro law and ideal gas equation. Thank you.